Welcome. I'm going to show you how to use free body diagrams to solve the simplest of problems, which is an elevator problem. Okay, so we're going to use these same forces that we've been using, uh, and we have to think about what forces would be on you as you stood inside of an elevator, right? So I'm going to represent you with a box because that's how I roll. Okay, and you have to think about what forces are on you while you sit in an elevator, right? Okay. Well, gravity is a good one to start with because you always have a gravity force on you, and that's going to be acting straight down, and we give that with F sub G, all right, force of gravity. Now, when you are in an elevator, there is a surface supporting you, so there is a normal force, and since the floor is horizontal, there is going to be a perpendicular upward normal force supporting you, right? Remember, normal means perpendicular. Okay. Now, this is going to be true for every person in an elevator, okay? That there is going to be a gravity force down and a normal force up from the floor, as long as you're in an elevator. Now, because the elevator is not always at rest, then these will not always be balanced, okay? But they will always look like this. Now, the whole point, now again, we don't have any other forces, right? So you could call the floor force a normal force or an applied force. I'm calling it a normal force because if there was friction, it would allow us a little bit of freedom to use that formula that relates friction and normal forces. But you could call the floor an applied force. There are no strings on you while you're in an elevator, so there's no tension force, and we're going to ignore friction, so there's no friction force. Okay, so we've got our free body diagram, and this is, like I said, going to be the same free body diagram for all elevator problems. Now, the whole point of your free body diagram is to write a specific form of Newton's second law, F net equals ma. And we only have to deal with one direction here because we've only got the vertical direction, so we don't have to worry about y direction at all. All right, now looking at our picture, I have two forces that make up the net force. Remember, net force is just a fancy word for the sum of all the forces. I have a normal force and a gravity force. Now, I certainly expect the gravity force to come out to be negative because it's down, but I'm not going to bother to put in the negative now. I'm going to wait until I put numbers in. There are times where you might want to do that, but this is not one of them. All right. So, excuse me. All right. Sorry. Okay, now, what if we had some data here and we actually wanted to solve this? And usually what we're trying to solve for is the acceleration of the elevator. Well, let's see a couple of things. Let's say we've got the mass of the person riding, and I'm going to use the mass of a typical high school student, which is 60 kilograms. That's akin to about 150 pounds. And let's see, what else we might know is that the force of the scale. So let's imagine the way these work is you'll often have the person in the elevator standing on a scale, and then the scale force actually has a reading, right? So let's say the scale force reads 400 newtons. Now, can I use this to figure out the acceleration of the elevator? Now, first of all, you have to remember that mass is not weight. So part of the problem here is going to be determining the weight force from the mass. And to do that, I'm going to use the formula Fg equals mg. That's right off the front of your reference tables, or actually the mechanics page on your reference tables. I'm kind of looking for that and not finding it in a hurry, so I'm not going to grab it for you right this second. Okay, so let's plug and chug into here. So F sub g equals 60 kilograms, and little g is negative 9.81 meters per second squared. Okay, let's actually figure out what that is. And I get that the weight force is negative 588.6 newtons. Circle that because it's an intermediate value. Okay, so typical high school student has a mass of 60 kilograms and a weight of around 600 newtons. In this case, exactly 588. Okay, so now I can plug these two pieces of information into the free body diagram formula that I just came up with. Couple things to remember. First of all, you may think that the scale tells you your weight, but it doesn't. One of the hard problems about elevator problems is the force of the scale equals the force normal. Turns out scales don't tell you their weight, your weight. They tell you how hard they have to work to push up and to hold you there, which is technically the normal force. Now, in your bathroom, these two forces are going to be balanced because you're not accelerating, but that's not true in an elevator. Okay, so let's actually take this and plug it into our formula. All right, so I'm going to rewrite that here. So I have normal and gravity equals ma. Okay, technically in the y direction. Okay, the force normal is the scale force. That's this, 400 newtons. And that is an upward force because the normal force is a supporting upward force. And then the gravity force is negative 588.6 newtons. That's a downward force. And in general, we're going to say anything down or left is negative. Equals the mass. That's still 60 kilograms. And we're solving for the acceleration. I can do the math here. And I get that negative 188.6. I'm going to drop units is 60A. And so I get acceleration is negative 3.14 meters per second squared. Okay, so see what we did. We drew a free body diagram, labeled all the forces. Use that to write a specific form of Newton's second law. So in this case, for elevators, normal and gravity equals ma. And by the way, this works for all elevators. Okay, then I figured out what my weight force was by plugging it into Fg equals mg. And I put in my scale force and I solve for acceleration. Now, the last part of these problems is trying to say, are you at the beginning, middle, or end of your ride? Okay, let's say this person is going down. They would have to tell you that. Okay, I can't tell from the forces. Now, if you are going down, notice that this is bigger than this, right? So force normal is 400. And the force of gravity is negative 588. So this is definitely a much bigger force. Okay. So we should also note that the F net is down. Okay. Because the bigger force is acting in the downward direction. Newton's second law says acceleration and net force will always be in the same direction. So therefore the acceleration needs to be down. And it's also going down because that is a given. Okay, now, if your velocity is down and your acceleration is down, this is speeding up. Whenever the acceleration or the force is in the same direction as the velocity, that's speeding up. Guess what part of the ride you speed up on? The beginning. So this person's at the beginning of their ride down. If, however, all right, if we had a different situation and instead they said, forget that, now we're going up. Okay, so let's pretend we're going up. But we have these same forces. Well, the velocity would be up. The acceleration is still down. The net force is down because net force and acceleration will always be the same direction. Okay. And so if you're going up, but your acceleration is down, this is slowing. And so this would be the end of the ride. Remember, on a typical elevator ride, you're going to speed up in the beginning, then you'll go for a constant velocity for a while, and then you'll slow down at the end. All right, hope that helps. Good luck.